Right, let's look through this 2018 Unit 3B. So question 1 is about this resistor here and an experiment that was being carried out on it. You've all read it, you don't need me to read through it. So part A gives you an analog display. That's very similar to the wee, if you remember back to junior school, the wee blue meters we would have used where there's 2 scales on it. So it's really easy to accidentally read off the wrong scale. So you need to be careful in questions like this. So using all the information you've been given, decide which scale was being used in this case and give the reason for your choice. So this was measuring what? Voltage? Yeah. So it reads up to a maximum of 10 volts. So it's either going to be the reading is either going to be about 4 or about 8 volts. But it can't be 8 because see if you look back up to the very start here, in this case the component is across a fixed 4.5 volt DC supply, so this is only 4.5 volts. So there's no way that this resistor can be reading 8 volts. So they must be using the bottom scale on that one there. So the scale is the 5 volt scale. And the reason is that the other reading is 8 volts, which is larger than the 4.5 volt supply. Or you could just say that 4 volts is less than the 4.5 volt supply. Okay. So part 2, using the scale you've chosen, state the voltage reading and the absolute uncertainty. So I looked at it there on the previous page. 4 volts was the one it was closest to. This is what I would put for my answer, plus or minus 0.1 volts. I suppose it's the only thing you really can put. So really, again, they're testing, can you figure out what these mean? So we start off nice and easy in these questions. So the smallest increment on this scale here is 0.1. Now there would be an error carried forward. So if you put the 10 volt scale here and you were reading off the top line, your answer is going to be 8. And then the plus or minus is going to be 0.2, because on this scale the smallest increment is 0.2. It's going up in 0.2s. Does that make sense? I'd like to think it does, right? So then a digital ammeter is used and it gives a reading of 0.23 amps. What's the absolute uncertainty? Smallest increment. Because this goes to 2 decimal places, it's going up in 0.01. Easy. Part 2. Use the voltage and current readings to calculate a value for the resistance. So you've got your V and I. You can easily calculate resistance here. This is what you should get. Again, there would likely be an error carried forward if you'd put 8 up here. Then you need to apply your rules for uncertainties. So remember to calculate the absolute uncertainty here for resistance, because you're dividing voltage by current. Anytime you're dividing, that means you add the percentage uncertainties together. Okay, so this is really the order that I would work in, down here and then down here. So the first step that I would do would be to calculate the percentage uncertainty of the voltage, which is the absolute uncertainty divided by the reading. Gets you that. Then calculate the percentage uncertainty of the current. Again, the absolute uncertainty over the reading. Gets you this. So there's 1 mark for getting both of these values. Then applying your rule, so the percentage uncertainty of the resistance is going to be the percentage uncertainty of voltage plus the percentage uncertainty of the current. Adding those together gets you that. So once you have the percentage uncertainty of the resistance, then you have to go and work out the absolute uncertainty. So really we're just finding 6.85% of 17.4, and that's what I'm doing here. That gets me 1.19. And yet there would be error carried forward for this because I've written this in. As long as this is consistent with the values that you've used, you're fine. Here, your answer had to be given to either 2 or 3 significant figures. Okay, anything more than that and you would have lost that mark. Right, let me see, part 3. Why is it better to refer to an uncertainty rather than an error associated with this reading? I would say this is a very common mistake. I'm guilty of it. A lot of people are guilty of it. We talk about like percentage errors all the time, but really we shouldn't. It should be uncertainties. And this is the reason. So error implies a mistake has been made, like you've done something wrong. This person didn't do anything wrong. But uncertainty refers to the range within like a reading can be taken to. So there's a range within which the reading is considered correct. Or if you've written anything like equivalent to that, if what you wrote means this in different words, that's obviously fine. Right, part C. The fixed DC supply is replaced with a variable DC supply. Explain how you would use this and why it ensures your value for the resistance of the component is both reliable and accurate. So because you now have a variable supply, it means you're going to be able to take multiple readings. So you're going to be able to change that input voltage and take, like the way we did every single electricity experiment this year. We varied the input voltage and we took various readings, and then we were able to plot a graph. That's basically the answer, but let's look at the proper wording of it. So you're able to take multiple readings of voltage or a range. That gets you 1 mark. It means any anomalous results can be identified and ignored or discarded. That's the 2nd mark. I have a feeling if I was answering this, this is the one I would forget to put in. And then the last mark is for saying once you have a range of values, you can either then just calculate an average, or this here is a better answer in my eyes because it would be written more often. So then you can plot a graph with axes and you can use your best fit line or your gradient to, or sorry, the gradient of your best fit line to calculate the resistance then. So I would go for this, but they did also accept that. Right, I'm rambling, move on. Right, question 2. A pendulum undergoes simple harmonic motion. Whenever I was looking through this before asking you to do this, I sort of panicked thinking, oh, I haven't done this yet, but actually the question ends up being okay. Anyway, a pendulum undergoes simple harmonic motion after it's been displaced to one side and allowed to swing freely. A motion sensor is used so that a graph of displacement against time for 2 complete oscillations can be displayed. And we've got an example of this graph here. So the one bit of information I had told you on the stream in Google Classroom was that with simple harmonic motion, all simple harmonic motion is like something like a pendulum. It can also be like a spring, something on a spring going up and down, that the time period for one oscillation is consistent. So even if it's swinging from here to here, this is probably going to be blurry in the video, or if it's swinging from here to here, the time period for both of those is going to be consistent. So remember, time period just means the time for one complete swing. Okay, so and one complete swing would be from here to here. Okay, right. Anyway, first part of this is by finding, that even tells you to do this, so by finding the gradient of a tangent to the curve. Sorry, I said that like this because this year, whenever the year above you were doing this, most of them forgot to do the tangent bit here. So by finding the gradient of a tangent to the curve, use this diagram to determine the size of the maximum velocity of the pendulum, and then state one time at which that maximum value occurs. So this is a displacement time graph. You need to remember that the gradient of a displacement time graph is the velocity. So the maximum velocity is going to happen whenever the gradient is steepest. So that's going to be here. You could also choose here, but it doesn't matter. Here or here I would go for. So there's my tangent there, right? The red line is the one I drew on, and then these 2 points are the points I chose for calculating my gradient. Okay, so my calculation's over here, and this is what I got. But the mark scheme didn't give any values. So there's 3 marks. There's 1 mark for having your tangent drawn to your curve. There's 1 mark for having the value calculated from your particular tangent. Now, I have not marked yours yet. There's, again, as I'm recording this, there's only a couple of them have been handed in. But I'm going to guess that this is going to be hard for me to mark. So we'll see how I get on. And then the time's either going to be any of these, so 0.5, 1.5, 2.5, 3.5. So here's the 0.5, that's whenever the graph is steepest. 1.5, 2.5, 3.5. Okay. Part 2. Determine the minimum velocity of the pendulum and state one time at which this occurs. So velocity is the gradient. Minimum gradient is going to be whenever it's horizontal. So that's why the minimum velocity is 0. So it's either going to be here, or here, or here, or here, or here. So that's all the times that they would have accepted there. 0, 1, 2, 3, or 4 seconds. So you're looking to see what's the smallest gradient, and in this here, that's going to be the horizontal gradient that you get at that peak in the trough. Okay, part B. Same pendulum is set in motion a second time with a smaller initial displacement than before. So this is the question that you needed to know, that the time period remains constant no matter what the amplitude of the oscillation is. So on this diagram, sketch the graph of displacement against time for the new motion. This is what the marks are for, and I'll go over and show you mine. It's not particularly great, but it would have got the marks. So you needed to have 2 complete waves, time period remaining the same. Doesn't necessarily have to be in phase. I think you'll know what I mean by that by the stuff you've done with Mrs. Turner this year. And as long as your maximum displacement was smaller. So same time period, but smaller amplitude because hasn't been released to as high a height. So this wee one here is my answer. I'm not particularly happy with that curve. It's a bit pointy for my liking, but I think it would have got the marks. Just about. So as long as your peaks and troughs are smaller than the original, and as long as the time for one complete wave is the same length as the original, which is why I think it's easier to just line up the peaks and the troughs with the other one, and then you can just join them up. Then, how will the magnitude of maximum velocity for the second motion of the pendulum compare with the maximum velocity of the original motion? So maximum velocity is at the maximum gradient. You can already see my answer, it's going to be less. The reason for that is because the horizontal distance between peaks and troughs is going to be the same, but because it's not being stretched up as high, then it's not going to be as steep of a curve here. Also, if the time period is staying the same, so the time for one oscillation is staying the same, if it's going from here to here to here in the same time as it's going from here to here to here, then obviously this one's going to be faster, and the one with the smaller smaller amplitude is going to be slower. Okay, so number 3, a CRO is used to measure the frequency of sound waves produced by a vibrating tuning fork. The signal from a microphone is connected across the Y input for the CRO. So I feel like in this question you'll probably be better than me because you're more familiar with waves and all that stuff, because you have been doing that with Mrs. Turner this year. It really is a while from I have done all that wave stuff at A level, so you should be better than me at this stuff. Anyway, that means, by the way, that if I can do these questions, you can do these questions. So from the CRO display, determine the frequency of the tuning fork that is being used, and you're told that the screen is 10 centimeters wide and the time base is set to 1.5 milliseconds per centimeter. So every one of these is 1 centimeter and the time base is 1.5 milliseconds per centimeter. So there's a couple of different ways that you could do this. Because there's 10 squares across here, this is 10 centimeters, and you're told that every wee centimeter is 1.5 milliseconds. The whole screen is 15 milliseconds, so the time from here to here is 15 milliseconds. Then if you count how many waves there are, so one, oh, I've lost track already. There's one, isn't it? No, there's one. 1, 2, 3, 4, 5, 6, 7.5. So 15 milliseconds for all the waves. So if we divide by 7.5, it tells us that each wave is taking 2 milliseconds. And then if you use F equals 1 over T, you'll be able to get the frequency. So F equals 1 over T. The time period is 2 milliseconds, or 2 times 10 to the minus 3. That gives you a frequency of 500 hertz. And there would be an error carried forward for your whatever you got for your time period. So if you got this part wrong, you can still get 2 marks for those bits there. So for this one, the Y sensitivity is set at 2 millivolts per centimeter. What's the peak voltage of the display? So if we look back here, the voltage is going to be from the equilibrium position up to the maximum. So each one of these squares represents 2 millivolts. So we've got 1, 2, 3, almost 3.5, which then we have to multiply by 2 millivolts. So they would have accepted anything in the range from 6.6 to 7 millivolts. Okay. How would you expect the display to change over time as the tuning fork continues to sound? So it's going to get quieter over time, so that means the amplitude is going to decrease. And if you mentioned anything else about the time period or the frequency, it must be correct. So even if you said this and then you said the time period would decrease, you wouldn't get that mark, because the time period is going to stay the same. The frequency is going to stay the same and the time period is going to stay the same. The only thing that's going to change is the amplitude, because it's going to get quieter. Right, lost my pencil. For part 4, here, sketch the display you would see if the time base is switched off. Honestly, I'm not sure if you will have been able to answer this or not, but with the time base being switched off, well, when the time base is on, if you think about your little dot on the CRO screen, and it's vibrating up and down just with the frequency of what it's displaying, but the time base means that it's also moving across as it's doing that, which is how we get this wave pattern forming. So if the time base is switched off, your little dot from your CRO is just going to vibrate up and down the way on the one spot, because it's not moving across as it's doing that. So it's literally just a vertical line, but if you can see in the answer here, it has to match the amplitude of the one before. So it was 6 squares and then a little bit either side. So the mark scheme had said 1 mark for having a vertical line, the second mark for matching the amplitude really, which was 6.6 to 7 centimeters. For this, because this is like a scanned in version I'm using, this probably isn't actually a centimeter anymore. So for mine, oh flip me, it is actually a centimeter. I was going to say for mine, as long as it matches the number of squares, we'll be fine. Okay, number 4. This one, again, tricky enough. So Geiger and Nuttall proposed a theory relating the half-life, T1/2, in seconds of an alpha emitting nuclide to the energy E in mega electron volts. So he's relating these two things, the half-life and the energy of the emitted alpha particle. The theory is expressed here, so this is the equation for this question. State what the unit abbreviation MeV stands for, mega electron volts. Now part 2 is tricky enough. So this is like what we did at the very start of this year, but like taken up a notch. So state the unit of each of the constants A and B. Now look back to your original equation. So your original equation is log of the half-life equals the constant A multiplied by the energy to the power of -1/2 minus B. So log of T1/2, log of the half-life, log of anything has got no unit. So because the left-hand side of the equation's got no unit, the right-hand side of the equation has to also have no unit. And that means every single term here has to have no unit. Hold on, get my dog out. Right, I'm back. So what was I saying? So because this side here has got no unit, then this side has to have no unit, which means every single term, and remember terms are separated by pluses and minuses, has to have no unit. So this has to combine, these two things multiplied have to combine to give you no unit, and this has to have no unit. So first of all, that's why B is no unit. For A, well, see the way in the equation E is to the power of -1/2. the power of minus a half is going to also apply to the unit. It's harder to get your head around that with stuff like this that looks a bit more awkward, but if you think about it, if you have an equation that has time squared in it, the units of that is going to be seconds squared, so the power has applied to the unit as well. So this means, I'm going to expand this out here a wee bit, E is measured in mega electron volts, so this is mega electron volts to the power of minus a half. That's getting multiplied by A. So for these two things to combine to give you no unit, then whenever you're using your rules of indices here, whenever you multiply, you have to add your indices together. So A has to be in mega electron volts to a half, because whenever you multiply that by mega electron volts to minus a half, then you end up with nothing. Yeah, sorry, took me a minute there, because I couldn't think how to explain it. Because whenever you multiply two things together, you add their powers together. So a half plus minus a half is going to give you mega electron volts to the power of 0, which is 1, so no unit. So that means A has to be mega electron volts to the half. That bit's tricky. Okay, and even if you're one of the people that is sitting looking at the mark schemes for this, you better be watching these videos so that you can understand that. Think I'm not onto you. Part B. So this table gives the experimental values for E and T a half for some alpha emitting nuclides, so there they are there. Values for E to the minus a half and for log of T a half have been calculated. So these are the two things that were measured, and then these are the calculations that have come from it. So have the values of E to the power of minus a half been recorded correctly? Yes. These are to the same number of significant figures as the E values were. So these are the 3 significant figures. These are the 3 significant figures as well. Then on for part 2, draw the graph of log of T a half against E to the minus a half. Scale the axes appropriately, plot the points and draw the best fit line. Now, this scale was so annoying. So again, I have chopped my page up so that I had the same number of squares as was in the actual paper. So there was 10 squares vertically. Now, I've ended up going with a scale of 4. I hate scales of 4. They're allowed, they're fine, but I just personally don't like them. It also means that in this one here, my points honestly are borderline for taking up at least half the space. So this is to about here. So I'm about 10.5 centimeters, and the maximum amount of space I had here is 20. Oh, you can't even see that properly, sorry. But it's just about right. I would have preferred to go in 2s, but that just didn't fit. Anyway, ignore these red points, they were for that bit later on. This is my graph. Yours might be different, as some of you seem to be doing the graphs even on fine paper, and as long as they're roughly right, then that is fine for now, obviously. But that it should give you a pretty decent straight line. Here's what the marks are for. So one for the X scale, again, so your points are taking up at least half the space. Y scale, same rule. Both axes labelled correctly, hopefully then from last week. So last week most people were labelling things like this incorrectly. Hopefully you have learnt from that. And you have these labelled properly this week. 2 for your points, and then 1 for your line of best fit. Okay. Ooh. Part C. Right, this little table here, let me get that graph out of my way. This little table here gives you 2 values for E, so it gives you these 2. For part 1, ignore this bit for now. Enter the corresponding values for E to the minus a half in the second column. So that is just typing that into the power of minus a half, and it gets you this. There's 2 marks here, 1 each. They must be the 3 significant figures. Okay, to match the table previously, and because these are the 3 significant figures. So if they're not, you don't get them even if they're technically right. Part 2. According to the Geiger and Nuttall proposed theory in that equation from earlier, these are the values for A and B. Use these to calculate the theoretical values for log of t1/2. So you need to substitute with these and this e value, is it e in the equation? E to the minus a half. E to the minus a half. And that into your equation, and this is what you should get. The range that's allowed here will be because of, I would guess, because of if you'd left this original number in your calculator and used it to calculate that, it's going to give you a slightly different answer than if you just tick that in. So each value has to be correct, and you get error carried forward from these here. Significant figures were ignored for this here, so you weren't penalised for significant figures here. For these ones, because it's a calculation, I would go to 3 significant figures, but they weren't fussy about it in that one. Part 3. On the graph here, plot the 2 theoretical points from table 4.2, so the one up here. Join the points of the straight line and label the line GN. I didn't actually draw my line on in the end, but they're my 2 points, so you should have a random line labelled GN. Points correct, and your line. Then, part D. You should find your line from the experimental results is not very good, is in not very good agreement with the line GN. The values of A and B do not work well for those ones that were listed. Use your graph to determine a numerical value for A, which corresponds with the data in table 4.1. So that is for your original data, wasn't it? Isn't that what 4.1 was? Yeah, the original data. So that's the gradient of your graph. 1 for calculating the gradient. 1 for using a large triangle, remember the rule about 5 centimeters, and putting the correct values into your gradient equation. Remember, do not choose points, pick points on the line. Like, don't choose points from the table, pick points on the line. And then 1 for your gradient, and if it's between these two, that's your quality mark really. Part 2. Determine the percentage difference in the numerical value for A that corresponds to the experimental. So their A means your A, so whatever value you got for A, take away 148, because that's what it gave you in that question, or the other way around, doesn't matter which order, as long as you find the difference between the two. Then that's great, there's 1 mark for finding the difference. Flip, I'm awful rambly today. Then the difference over, and they accepted either here, so either the difference over your A value or the difference over the 148 multiplied by 100 calculated correctly to get that percentage difference. Okay, that is it.